So we're on page 407. We'll finish up section 4.2. Jake is taking the trip of a lifetime, heading to London for a week in the summer. His parents gave him $500 spending money. When he arrives, he sees the following currency exchange rate information. Reading across the first row on the table, he can find what $1 US is worth in the United States, in Europe, in Great Britain, in Japan, in Canada, and in Australia. The remaining rows indicate what 1 unit of the other currencies would be worth in the listed countries. So number 3 is there's A through E. Work together on those, please. See if you can figure those out. So part A, why is there a 1 in each row?
That indicates the number, like one of their type of money, right? Is what I'm trying to say. It's
In their own country.
yes.
I would have a common rate of currency for each country shown.
Same thing. Part B. How much was $1 worth in London on this day?
I put 06.42. 0.642.
Convert Jake's $500 to British pounds. So like we did on Friday, we can put the $500 over 1. We can use the conversion fact that we had in part B. $1 is 0.642 pounds, so we need the $1 in the denominator and the 0.642 pounds in the numerator. We can cross off the dollars and this becomes a multiplication problem. What's the answer?
$321.
300
Pounds.
Yep, there you go. 321 pounds.
Why do we use that row instead of the column?
There is another conversion factor, and which one did you use?
I just did 500 divided by 1.559, and if I would have rounded, I would have gotten
Divided by what? I'm sorry.
1.559.
It works. You'll be close. You could actually use either conversion, but usually if you have a choice between multiplying or dividing, it's better to multiply. Any other questions? Okay, letter D. Analyze the calculation made in part C to determine a quick rule for converting dollars to pounds. Rules like this helps travelers make quick conversions without paper or possibly even calculators. Instead of setting up the ratio, what could you do? Well, since you've done one of them with the ratio, now you know for any dollar amount, you just have to multiply by 0.642. Does that make sense? So you don't really have to set up the ratio as long as you know that. So that would be a bit of a
You're going to
shortcut.
do that in your head, seriously.
I agree. But it is a little bit of a shortcut as opposed to setting up the whole ratio each time. To me, it's better than the other part that they have to this, the other part of the answer. They say, essentially, we are taking a little more than 60% of the number of dollars. A quick mental math approach is to take 2/5 of a number, divide by 5, and multiply the result by 3. 3/5 of a number. 3/5 is the same as 60%. I really don't think anyone's gonna do that either, convert 60% to 3/5 and multiply by 3/5. I don't think
In
they're
their
gonna.
head?
Yeah, I don't think anyone's gonna do that either, so I like this answer better. Part E. Which is a larger unit of currency, a US dollar or a British pound?
The dollar, isn't it? Well, yeah, it has to be the dollar. Because a dollar is 1, and the
Yes,
British pound is 0.642.
yes,
So it's not quite 1.
yes.
It's over. See, I don't know.
But we're talking about the unit. So the British pound is actually larger because it doesn't take a whole 1 to equal a dollar. The unit itself is
Okay.
larger.
Okay.
Okay, next page, the lesson wrap-up. What's the point? When unit conversions become difficult, dimensional analysis can organize and simplify the process. What did you learn? How to convert units using dimensional analysis. How big is big? How big does a conversion problem need to be to make dimensional analysis worth the time? Pardon me? Some people find it really helpful even if there's just the one conversion, like we just did with the dollars and pounds. Some people just like to use it all the time. Other people like to, at that point would say, no, I'd rather just multiply or divide. Some people would say, I don't want to use it unless there's 2 or more or 3 or more conversions. So it kind of depends upon the person. It is a real good way, though, to know whether you need to multiply or divide. Section 4.2 homework, My Math Lab and paper homework. Section 3 starts on page 410. Little Giants. Number 1, according to the U.S. Geological Survey, the Himalayan mountains rise over 1 centimeter per year. Find the rate the mountains are rising in miles per hour. So work together, see if you can figure that out. So we're starting with 1 centimeter per year. So we have a rate. We want to end up with miles per hour. So from centimeters, where do we go next?
1 meter to 100 centimeters is what I did.
We could, but we've been using the conversion 1 inch is 2.54 centimeters to convert back and forth between the US and the metric. 2.54 centimeters is 1 inch. You should be able to do it the way you were doing it also, Cindy. You were going to kilometers and then changing to miles.
That's what I did.
That should work too. You should, might be off
But
a
this
little
is
bit
the
due,
way
it might be off a little due to rounding, but
Okay.
really which one is off? Because they've both been rounded.
Okay, because that's the way I mean, I phrased it the wrong way, but
Should be about the same, I think. So from inches, where do we go next? And there's 12 inches and 1 foot. We can cross off the centimeters, we can cross off the inches. If we stop there, we'd have feet per year. Next part. From feet to, we don't have to go to yards. We can actually skip that one. We can go right to miles, yeah. How many feet are in a mile? There you go. 5280 feet in 1 mile. So we have the miles. Now we have to convert the 1 year to hours. So how do we do that?
Are you gonna go to weeks? And then
We can skip weeks. How many days are in a year?
365.
Okay, so 1 year is 365 days. You can cross off the year. At that point, we would have miles per day. Now what? We want to get to hours.
It's 24 hours in a day.
24 hours in a day. So, multiplying straight across in the numerator, and we get 1. What about the denominator when you multiply straight across? Get a really big number?
Yeah.
1,409,785,344? Divide that out. What do you get? No, not if you're taking 1 and dividing by that number. Did you get a really strange thing in your answer? What did you get?
7.09327845 minus 10.
Okay. So if we round that decimal number, we would have 7.09, right?
Here. Minus 10.
Now the minus 10 at the end
Power, isn't
is the power. It's such a small number that they've given it in scientific notation. But that's what it means. It's times 10 to the negative 10 power. The label would be
Miles per hour.
miles per hour. So we're actually going to be working with scientific notation today as well as these conversions. Number 2. A mountain range encompasses glaciers which store approximately 10,000 cubic kilometers of fresh water. Convert the volume to cubic inches. So we've been using centimeters and inches, so we're going to have to convert the kilometers to centimeters first. So kilometers to centimeters will be 1, 2, 3, 4, 5 places to the right. However, it's just not kilometers and centimeters, it's cubic kilometers. So what are we going to have to do with that 5?
Take it to the third power?
What did you say? One more
Take
time?
it to the third power? Or no?
You're on the right track. We would multiply by 3. So what that means is 10,000 cubic kilometers. We would have to move the decimal point 15 places to the right makes that a huge number. Let's see. We could write it in scientific notation. The decimal point would need to be right after the 1. Do you agree? To write it in scientific notation? We haven't talked a lot about scientific notation yet. But the decimal number has to be a number between 1 and 10. Okay, so it has to be a decimal where there's one digit other than a 0 in front of the decimal point. So 1 point something, 7 point something, 9 point something. So in this case, we would have 1 or 1.0 times 10 to some power. Well, we have the 15 from over here, but there's also 4 decimal places over here in 10,000. So 4 plus 15 would be 19. That actually is our exponent. So that was crazy, just changing to cubic centimeters. Any questions up to that point? There's 4 decimal places over here in 10,000, and then the 15 in the conversion. So we have 1.0 times 10 to the 19th cubic centimeters. We want to change to cubic inches. What's the conversion between centimeters and inches? Mm-hmm. 2.54 centimeters is 1 inch. But now be careful, because we need cubic centimeters, which means we have to cube everything in that conversion factor. So now we can cross off the cubic centimeters. 1 cubed is just 1, so we still have 1.0 times 10 to the 19th in the numerator. In the denominator, we have to take 2.54 and cube it. What is that number cubed? I think it's 16 point something, is that right? 16.387064? And this would be cubic inches. Well, this is going to be easier to work out if both numbers are in scientific notation. So again, we need the decimal point between the 1 and the 6 to be in scientific notation. So 1.638764 times 10 to some power. We have to figure out what the power is. Now going from 16 to 1, the decimal part becomes smaller, right? Which means the exponent needs to get larger. So it wasn't really a 0 before, it becomes a 1. Which makes sense. If we take the smaller number, 1.638764, if we multiply by 10, it's going to make the number larger. And multiplying by 10 just moves the decimal over 1. So if we're decimal point starting out here, we multiply by 10, it's just going to move it over to there, same number we had before. Now, to divide decimals, or divide scientific notation. I can tell you're loving it today. Okay, we're going to start with the decimal parts. So take 1 and divide by that long decimal in the denominator. .61023744409. Okay. And now we'll take care of the powers of 10. Notice we have the same base. Do you remember what we do with the exponents when we're dividing? We're dividing and we have the same base. What do we do with those exponents? Subtract them. 19 minus 1 is 18. Now that number is not in scientific notation because we would need the decimal point to be between the 6 and the 1. And let's also at this point round it 2 decimal places, so 6.10 times 10 to some power. And this time from 0.6 to 6, the decimal's becoming larger, so the exponent's going to get smaller. What do you think the new exponent would be? Not -1, but we subtract 1 from what we had. If it starts out at 18, subtract 1 would be 17. Wow, that one was crazy. Any questions? Most calculators will give the answers to the last 2 problems in a form known as scientific notation. Scientific notation is a shorter way of writing numbers that are too large or too small for all their digits to show on the calculator. It is also a convenient shortcut for writing large and small numbers by hand. Number 3. Refer to number 1. Was the answer a small or large number? The answer to number 1, was that a small number or a large number? It is a small number. What was the sign of the exponent on 10? What was the sign of the exponent on 10? Sorry? Negative. Number 4, refer to number 2. Was the answer a small or large number? That is a large number. What was the sign on the exponent on 10? Positive. Questions on 3 or 4? So when a number is in scientific notation, if the exponent on the 10 is if the exponent on the 10 is negative, then you have a very small number. If the exponent is positive, then you have a very large number. Let's read in the box about scientific notation. When a number is written in scientific notation, it will look as follows: a times 10 to the nth power. The size of a must be a number between 1 and 10, but not equal to 10. A can be positive or negative. Mathematically, this is written: 1 is less than or equal to the absolute value of a is less than 10. N must be an integer, and therefore can also be positive or negative. So then they give us this table. In the examples column, those are all in scientific notation. But the counterexamples column, those are not in scientific notation. So what's wrong with the first example, the 550? Why isn't that one in scientific notation? It's not being multiplied by 10 to some power, and also the decimal point would have to be between the 5s. How about the second one, 79 times 10 to the negative 4th power? What's wrong with that one? The decimal point is in the wrong place. It should be between the 7 and the 9. What's wrong with the third one? 0.9 times 10 to the 12th. No, not negative. Where should the decimal point be? Well, it's after the 0 right now. Where should it be?
I said in front of the 0.
Oh, no, wrong way. So instead of moving left, it should move right. So it should be where?
After behind.
Exactly. Remember, we always need 1 point something, 2 point something, 3 point something, or 9 point something. What's wrong with the last one? 1.2 times 10 to the 2.3 power.
You don't want a decimal point for your exponent?
Exactly, yep. The exponent has to be an integer. If a number is written by listing all of its digits and not using exponents, it is considered to be in standard form. So back in the counter examples, the 550, that's actually in standard form. Let's take a closer look at scientific notation. Example 1. Let's write 7 million using scientific notation. And I think I'm going to skip right to the last part of that. We're just going to go, in other words, we're going to go right to the scientific notation and not do the other stuff they want us to do there. So where does the decimal point have to be if we want to write this number in scientific notation?
After the 7.
Has to be after the 7. So we have 7 times 10 to some power. Is this a small number or a large number?
It's a big number.
Okay, so what's the sign of the exponent?
It's going to be a positive.
It's going to be positive. Now, how far do you have to move the decimal point to move it behind the 7?
1.
Not 1. Where's the decimal point at in 7 million? Where's the decimal point at the beginning? In 7 million?
There is a 1.
When you don't see one, where is it?
To the end of 1.
It's at the end. So now if you move it over so that it's right behind the 7, how far did you move it? 6. So there's 7 million in scientific notation. So far, so good? What is the significance of the exponent on 10?
That's positive.
It's positive because there's a large number, because it's a large number. But what else? Why is it 6?
Because the number is zeros. The number
It's,
you're
it's how
moving
far
it.
you had to move the decimal point, yep. Notice that 7 million is a large number, and its exponent, when written in scientific notation, is
Positive?
there you go. Example 2. Let's write the rate from number 1 in the Explorer in standard notation. Start by listing the answer from the calculator.
Ugh. I'm sorry.
So we had 7.09 times 10 to the negative 10 power. Is this number larger or smaller than 1? Smaller. We have a negative exponent, so it's a small number. Since the size of the exponent on 10 matches decimal point movement, how many places will the decimal point move in which direction? So how far is it going to move? Okay, so we're just going to say 10. That's how far it's going to move. Since it's a small number, which way are we going to move the decimal point? Left. So it's going to move 10 to the left. Write the result. So I'm just going to write the digits that we have so far, 709. The decimal point starts out after the 7. We need to move 10 places, so in front of the 7 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there should be 9 zeros there. You can put the 0 in front of the decimal point. That's optional. However, if you're in the nursing field, make sure you get used to putting the 0 in there. That's very important in the nursing field. Any questions on example 2? Okay, bottom of the page. The exponent on the 10 in scientific notation always tells you the amount of movement and the direction of movement of the decimal point when you write the number in standard notation. However, it might be simpler to remember the following. Okay, so I'm actually going to read the right side first. Size of number in scientific notation is small, less than 1. So the exponent in scientific notation is
-1.
not necessarily -1, but it will be negative. Depends on how far we have to move the decimal point as to what the number is. But we do know it's going to be negative. The next one. Size of number in standard notation is large, greater than or equal to 10. The exponent in scientific notation is positive. Size of number in standard notation is greater than or equal to 1 but less than 10. Exponent in a scientific notation is so size of number in standard notation is greater than or equal to 1 but less than 10. So maybe we have 1.05. What would the exponent be on the 10? In this case, we would not have to move the decimal point, correct?
It's just 1.
It would not be 1. What would the exponent be? It would be a 0. 10 to the 0 power is really 1. That one was a bit tricky. We hadn't talked about any like that. In practice, numbers written in scientific notation with an exponent of 0 and 10 are uncommon. Scientific notation is used to represent very large or very small numbers. If standard notation is easier to use, the numbers will simply be shown in standard notation. So what they're saying there is, if you do end up with something like this, they generally don't put the times 10 to the 0 power on it. They just write it in standard notation, say 1.05. Any questions? Page 413. How to convert from scientific to standard notation. Decide if the size of the original number is large or small by looking at the exponent on 10. If the exponent is positive, the size is large. If the exponent is negative, the size is small. Keep the sign of the original number. Number 2. Move the decimal point the number of positions indicated by the size of the exponent. Choose which direction to move based on whether the size of the number in standard notation is large or small. Number 3. Fill in the empty spaces created by the decimal point movement with zeros. So for example, 8.25 times 10 to the 4th is a large number relative to 10, since the exponent on 10 is positive. Since the exponent is 4, the decimal point must be moved 4 positions. Since the original number is large, the decimal point moves to the right. The 2 empty spaces should be filled in with zeros. So 8.25 times 10 to the 4th becomes 82,500. Any questions on that example? To convert from standard to scientific notation, number 1, determine if the size of the original number is large or small. If the size of the number is greater than 10, the size is large and the exponent on 10 will be positive. If the size of the number is less than 1, the size is small, and the exponent on 10 will be negative. Keep the sign of the original number. Number 2, move the decimal point until the resulting number is between 1 and 10, but not 10. This new number between 1 and 10 is denoted A. Note the number of spaces the decimal point moves. This number of spaces is the size of the exponent on 10 and denoted with a capital N. Number 3, write the scientific notation in the form A times 10 to the nth power. So for example, if we have negative 0.0025, it's a small number because the size is less than 1. The exponent on 10 will be negative. Move the decimal point to be between 2 and 5, creating 2.5. The decimal point moved 3 spaces, and the size of the original number is smaller than 1, so the exponent on 10 is negative 3. The answer is negative since the original number was negative. So negative 0.0025 becomes negative 2.5 times 10 to the negative third power. Do you have any questions on that one? Okay, the practice. Complete the table converting between scientific and standard notation. Okay, so the first one, 8.7 times 10 to the negative 4. Let's write that in standard notation first. Which way and how far do we need to move the decimal point?
To the left 4 times.
Exactly. So our digits that we're starting with is 8, 7. Now the decimal point started out between the 8 and the 7, so moving in front of the 8 would be 1, 2, 3, 4. So there should be 3 zeros between the decimal point and the 8. Any questions so far? Now how would we say that decimal number in words?
Isn't it hundreds, maybe 700 thousandths?
Well, okay. Well, first we look at the number as if there was no decimal points there. So it will be 87. Do you agree? That's the first part, like Drew said. And now we have to list the position of the last digit. So the first 0 would be tenths, the second 0 would be hundredths, then thousandths, 10 thousandths, and 100 thousandths. So Drew was right. $8,700 thousandths. Any questions on the first row? Okay, work on the rest of those, see if you can get them. Okay, so the second one down, we were just discussing that 10 to the 0 power is really the same thing as 1. So negative 7 times 1 is just negative 7. And in words?
Negative 7.
Negative 7. Now the next one, we have to move the decimal point 4 places to the right since it's a large number. 1, 2, 3, but we need one more place, so we're going to have to fill in with a 0.
Got a little strobe action going on.
Yeah, I see that. 87560. I wonder if it's recording that flashing. Guess we'll find out, huh? So, what is that number in words?
87,560.
I'm glad I'm not missing class today. I'd suck watching.
Okay, 5 trillion. Well, we have a 5. 3 zeros will be 5,000. 5 million. 5 billion. So there it is. 12 zeros. In scientific notation, well, we need the decimal point right after the 5. So 5 or 5.0 times 10 to what power? Negative 12?
Positive.
Positive
It's a very large number, so the exponent should be positive. The next one down, 1 millionth, with the TH on there means it's a very small number, it's less than 1. So we have 0 point, or just a point, tenths, hundredths, thousandths, 10,000ths, 100,000ths. The next position is millionths, so that's where we put the 1. That should be 1 millionth. So in scientific notation, how do we write that number?
Negative 1?
Is it negative?
No.
No, the number itself is not negative, so just 1 or 1.0. Either way there is fine. Times 10 to some power.
5.
Negative 5?
Well, first of all, is it going to be positive or negative?
It's going to be negative because it's a very small number.
Yes, exactly. It's going to be negative. So from here, we have to go after the 1. So 1, 2, 3, 4, 5, 6 to get the decimal point after the 1. So negative 6 should be the exponent. Then that next really large number we determined was quadrillion. That comes after trillion. So 3 quadrillion. Now in scientific notation would be?
It's going to be positive because it's a big number.
Yes, the exponent will be positive. 3 times 10 to the what? 15? Agree? That is correct. Any questions? At the bottom of page 413, they talk about engineering notation. I don't think any of you plan on being engineers, and even if you were, I would say you could learn that later. So we're going to skip engineering notation. So next page, page 414, cross off that last column where it says engineering notation.
Oh, not the whole thing.
Not the whole thing, just the last column, engineering
Just
notation.
trying to get rid of it all.
Which actually gets rid of the last 2 rows also.
Oh, yeah.
So work on the top 3 rows. See if you can do those. It's actually more review. Top 3 rows. 10,000, 16 trillion, 421 thousandths. So 10,000 in standard notation would look like that. How about scientific notation?
1 times 10 to the 4th.
Okay, 16 trillion.
You would have 16 and then you have 9 zeros afterwards.
16 with 9 zeros. So then in scientific notation would be
1 times
1 point what?
10, or, I said that wrong.
Would be that times 9 or 10 to the 9.
Wouldn't that only be billions though?
Let's see.
I think there should be 3 more
Thousand
zeros.
million. You're
Oh, yeah,
right.
I had it.
Yep.
Yeah.
3 more zeros. And then in scientific notation, we need the decimal point between the 1 and the 6, right? Because there can only be 1 digit other than a 0 in front of the decimal point. So 1.6 times 10 to some power. What would the power be?
12,
Not 12,
9.
not 9,
13.
13. So the decimal point starts out at the end. That would be 3, 6, 9, 12. 1 more is 13. 421 thousandths. How do you write that in standard notation?
Are we going to 04? 21.
0421, agree? Agree? Let's see, the first position would be tenths, the 4 would be hundredths, the 2 would be thousandths.
Yeah, so shouldn't it be 0.421?
Yep.
I keep
So we have an extra 0 in there.
Sorry about
scratching
that.
off this.
0.421. Well, once you think you have it, do what I just did. Go back through, count the positions. This would be tenths, hundredths, thousandths.
So that last number should be what you want.
The last number should say thousandths or hundredths or
Okay.
whatever, should be in that position.
Got it.
Okay, scientific notation.
4.21 times 10 to the 4th power.
To the negative fourth or third?
It would be negative.
Interesting. Well, the decimal point starts out before the 4, and we move it to after the 4. Negative 1. It's negative because it's a small number, but we only have to move the decimal point one place.
That's cool.
Okay, section 3 homework, my math lab and paper homework. Let's look at the lesson wrap-up. What's the point? Scientific notation provides a way to write very large and very small numbers efficiently. What did you learn? How to convert numbers between scientific notation and standard notation. How big is big? How large does a number need to be before you think it is worth using scientific notation? Really big, huh?
Big.
How large does a number need to be before your calculator must display it in scientific notation?
Would it be like
Millions?
10 to the
It depends on your calculator. Some calculators only have 8 digits in your display. Some have 10. I think most of them now have 10.
So you just say depends on the calculator?
Depends on your calculator. Yeah, how many digits will fit in your calculator display. Page 417. Cross off 10C at the bottom of the page.
I like that.
Yeah. That particular question, they're asking you to read the graph, and it